Okay, so in this movie clip, let's begin with the non-ideal effects at high V sub EB. In the previous movie clip, we have gone over the non-ideal effects at very low V sub EB. But in this lecture note, we're going to study what kind of non-ideal effects are expected at very high V sub EB. So again, please refresh your memory with non-ideal effects happened at very high forward bias for single PN diode. What kind of non-ideal effects did we learn? Yeah, series resistance, high level injection. So in this lecture note, you can see the same word, series resistance, high level injection. So in PNP BJT device, if I write down, draw the output current versus input voltage, common emitter configuration, this V sub BE is the input voltage, not output voltage. Output voltage was a V sub CE or V sub EC. That is output voltage, but now I'm talking about the input voltage. So if I draw the y-axis in logarithmic scale, then we're gonna expect this IC versus VBE, which is corresponding to the ID versus VG plot of MOSFET. Okay, so at very high V sub EB, the output current would be degraded. Okay, so that is ideal. This is real. So as output voltage, as input voltage increases, the output current has been degraded. I mean, the output current is not as high as expected. So what is the physical origin for that? Number one is high level injection happened in PJT. So because of very significant majority carrier diffusion current component happened, so that your output current has been degraded. Okay, so if your V sub EB is very high, your IC would be degraded. And the second physical origin for this, why the output current is degraded, is because of the series resistance existing in PJT. So your applied voltage V sub EB is, your effectively well applied voltage between emitter and base, denoted as a V sub EB prime, should be V sub EB, that is externally applied voltage between emitter and base, plus base current times base resistance. So this is a V sub EB is a voltage across emitter base junction, and this component, well, ideally should be ignored. However, this R sub B, series resistance in base, has come into the play when determining the applied voltage across emitter and base. So series resistance should be taken into account under high V sub EB. And the third physical origin for these non-ideal effects, I'm talking about this non-ideal effect, comes from current crowding, which has not been studied in PN diode. So let me draw the BJT cross section. So here P plus, that is emitter, and base, and N well, it looks like an N well, and the N plus tap has been fabricated to get base, and another P silicon, and a P plus tap for collector. So under active mode, the many holes would be injected into the base, this reason, and they are going to create the base current. And since this n-type base region has its own current resistance value, so this IB times also B, this IR drop would affect the effectively applied voltage. But here what I want to talking about is take a look at the whole flow. Previously, when we think about how the holes are moving across PNP BJT, the hole has been injected from P plus to N. However, in rear BJT cross-sectional device structure, the hole would be injected from bottom side as well as side walls. Okay, so many holes are flowing away from this small P plus emitter box. So very higher density of current at the edge of the emitter should result in very localized heating, resulting in very increased resistance value. Again, very higher density of current where at edges of emitters should result in what? Yeah, localized heating, and this would inducing increased resistance. Okay, so this current crowding is the unique non-ideal effects which cannot be found in single PN diode. All right, now let's switch gear and take a look at the Gummel plot, which is very widely used in evaluating the BJT device performance. So what is the Gummel plot? Take a look at the left-hand side and right-hand side. You're now looking at the Gummel plots. So I sub C output current of PNP BJT, and V sub B is input voltage. So the corresponding one for MOSFET is ID versus VGS. Okay. So here I have used the logarithmic scale for output current. So if I draw the ideal IC versus VBE, then the curve should be very straight line, all the way down and all the way up. However, if I measured output current versus input voltage, then you're gonna get this data point. I mean the blue colored line. And the black colored line indicates the base current. Ideally, base current wouldn't be modified, wouldn't be varied at all. However, at very low forward bias, I mean at lower V sub EB, as we have learned here in this slide, recombination current, right? The base current has been increased as expected. So beta DC gain has been defined as output current divided by input current, right? So this IB, the difference has been defined as beta DC for all input voltage. But from here to maybe here, in this voltage range, the beta DC is quite constant. So if I draw the beta DC versus IC, then very flat regime can be found from here to there. That is corresponding to this regime. However, your input voltage is very low or your input voltage is very high, then beta DC value has been degraded. Take a look at here because of what? Yeah, because of this recombination current in emitter depletion region, right? So this would have your beta value decreased. What about here? In this case, IB is constant, but output current IC has been degraded so that your beta has been degraded. Why is that? Yeah, series resistance and high level injection. Okay, so impact of high level injection in base and series resistance in base would degrade your beta DC value. Okay, so very high VBE because of high VBE, your upper current is also very high. Your beta value has been decreased. And if at very low VBE, low input voltage, your definitely output current should be very low correspondingly. So your beta has also degraded. So there would be the sweet spot, I mean the optimal operational window for your BJT. Okay, so in that sense, this gamma plot and beta DC versus I sub C is critical. Okay, so on the left hand side you can see the gamma plot, and on the right hand side you can see the beta versus IC. So this gamma plot, if you draw the gamma plot for your BJT, then you can, at a first glance, you can take a look at, you can catch what would be happened in your BJT device. Okay, so ideally beta DC wouldn't be affected by the input voltage, but in real, your beta DC value would have a very you know would be existing in a sweet spot position. Then now let's define the Gummel numbers for your BJT performance. I mean the when it comes to evaluate your BJT device performance, we may use Gummel numbers. Or when it comes to designing your BJT device, you may propose and suggest the Gummel numbers. So herein, for uniformly doped base region with negligible bandgap narrowing, because base is uniformly doped, but if base doping concentration is very high, then we should worry about bandgap narrowing issue. But herein, to make our life much easier, let's assume that a uniformly doped base region with negligible bandgap narrowing. Then the base Gummel number, G sub B, can be simply defined as NB, base doping concentration times, that is the physical width of quasi-neutral base region divided by diffusion constant in base region. I mean the minority carrier in base. In the case of PNP BJT, base is N-type, so minority carrier is Hall. So Hall diffusion constant in base can be used in defining the Gummel numbers. Okay. So if I doing some interpretation, the physical meaning of this Gummel number, then the answer can be found here. What does the Gummel number indicate physically? That means NB times W. That means a total integrated dose. NB is for unit volume how many dopant atoms are injected. But since I have multiplied the physical width of quasi-neutral region of base that in the unit of centimeters, so in the end, for a given area, how many dopant atoms can be found in the base? Okay, so majority carriers, those in the base, indicates this NB times W, and divided by what? Yeah, diffusion constant in base. So previously, when we are deriving the EVO small model for BJT, the upper current I sub C has been written with this equation. So here you can see that the Gummel number at BB divided by W times MB. Okay, so the inverse 1 over G sub B can be found in this equation for your upper current. So now, from now on, your upper current I sub C can be written with this equation. Q unit charge, A cross-sectional area of your BJT, Ni indicates 10 to the 10 at room temperature, and Gummel number in base, and how much input voltage, emitter base voltage, has been applied across your BJT. Then you can simply estimate your upper current I sub C. So this equation is corresponding to the IDS is equal to the 1 over 2 mu C ox W of L channel width channel length times VGS minus threshold voltage square. In microelectronic circuit class, you're very familiar with this scale law equation, and in MOSFET, right? So input voltage here and the output current. Let's go back to the equation above. Output current, input voltage. Okay, so MOSFET current versus voltage characteristic has been governed by square law. What about the current voltage characteristic of your BJT? Yes, this is the exponential one. Okay, so if I draw the ID versus VG in log scale, your MOSFET would show this shape of curve, and the subthreshold slope is very close to the 60 millivolt per decade, but not really. But in the case of BJT, if I draw the log I sub c versus v sub be, then since this is exponential term, so that you may see that the substrate slope of your BJT is quite same as 60 millivolt per decade at room temperature. Because your current versus voltage characteristic of BJT has been governed by this diode equation. Okay. All right. Now let's redefine the emitter efficiency gamma with Gummel numbers. Previously, when we have derived the emitter efficiency and alpha sub t, beta, and alpha stuff, those equations looks very complicated. And even the emitter efficiency, the equation for emitter efficiency was given this. Very many new numbers, so it's tough. But if your BJT uh, the base region has been well uniformly doped and no band-gap narrowing issue, then these two values would be identical, so they would be cancelled out. And in the end, you can see that here, Gummel number is defined as what? Yeah, MB times W divided by diffusion constant. So these three terms would be combined and written as G sub B. What about here? DE came to here, so this NE times W divided by D is defined as Gummel number in emitter. Okay, so GE is the emitter Gummel number. So once you know two Gummel numbers together, then you can simply define the emitter efficiency. Easy, right? What about the beta DC value? If I write down the full equation for beta DC, it looks like that. But if this W is much smaller than L sub B, the narrow base, which is preferred option to boost up the beta value in your BJT, so you can ignore this term then, and no band narrowing and the these two values would be cancelled out together. Then in the end, you can see that two Gummel number would give us the beta value. So the gain or how much gain are expected using your own BJT device, you should review what is my Gummel number. Okay, so in practice, this Gummel number can be simply defined as shown in here, doping concentration and the quasi-neutral regions width and diffusion constant. Those three key items are necessary in determining the Gummel number for each region base emitter collector. However, in practice, in real, the doping concentration or doping profile in base and emitter are not uniform in BJT device. In other words, the doping concentration in base and emitter follows and defined as a function of X. So, more general formula and equation for Gummel numbers are given as follows. Okay, so that this and that value would be obtained with a single integration. Okay, so more general formula for Gummel number is this. However, to make your life much easier, the GB is simply defined as this. Okay. All right. So I guess that's all for all contents that I would like to deliver you in this movie clip. I guess it's a good time to have a short break time. So in the upcoming movie clip, I'm going to tell you the modern, not here in the MPN, I brought it because I have taught you with PMP BJT, but just to refresh your memory, I guess MPN BJT structure is necessary, so I have brought the MPN BJT structure, and we're gonna see some conspicuous features uh, to be seen in this modern NPN BJT structure. Afterwards, we're gonna see the polysilicon emitter BJT. Well, previously I said all crystalline silicon material has been used in building up the BJT device structure. But what if we are replacing crystal silicon with polysilicon in the emitter region? What would be happen? What kind of benefits, advantages can we expect? Then we're going to redefine the emitter Kamel number with polysilicon emitter and bandgap narrowing issue and the narrow bandgap stuff. So what if we are going to use silicon germanium instead of silicon in the base region? What kind of benefits can we expect? So in that sense, people has developed heterojunction bipolar transistor, so HBT, okay? So in the base region, what if we are using narrow bandgap material? Then this not homogeneous junction, but heterogeneous heterojunction would give us some technical advantages in designing BJT device. So in that sense, HBT has been widely adopted and developed in industry. Okay, so we're gonna learn some more details, the HBT stuff in the upcoming movie clip. So see you in the next movie clip. Thank you for your attention. Bye bye.